Yeah, there's a book. You'll find them at Sam's. It's here, Serious Cryptography, and you can get a free copy from the library here. So if you just go to samsclass.info and then click 141, you'll find the book here. This is the main book we're using. All the cryptocurrency books are optional, and you can get a free copy online. Yeah, yeah. All right, good. Anyway, so here I want to point out, we already talked last time about the binary games, and now I want to point out these projects here. These are the only two that require Windows. These use a product called Cryptool, and so I've got a Windows cloud machine running someplace around here. There we are. This is my Windows cloud machine. I minimize there. You see our desktop down there. And here's, all right, so this is a Windows desktop running in my private cloud, and I've got Cryptool, which is strangely vanished when I minimized it, which is disturbing. Let's bring this back. And then, I wonder if Alt-Tab works. Probably not. Well, all right, I'll just try launching it again. Maybe it closed. Cryptool. There's Cryptool. Okay. And the point of this was used to teach cryptography to German bankers. And it's pretty cool to get practice doing cryptography. So you can use a wizard, which is the easiest way to use it. And then it will just let you go through various encryption routines and see how they work and see some of the attacks too. So I can do encryption, decryption, and I can use classic or modern algorithms. I'll start with classic. And then I can do, say, the Caesar cipher we've talked about. And so I can encrypt a message, like input your message here. So if I put in hello, and I give it a key of 3, which is the default, then let me make this as big as I can. All right, then I can go next, and it will encrypt it into KHOOR, so that's not too exciting. All right, and if I go back here, I can do various kinds of attacks on it. So let me just check my instructions here and see what I planned on doing. All right, so there's classic Caesar cipher, and so you do, get my instructions here. Okay, so do cryptanalysis, and let me see if I figure out a good way to scroll. There's a little lag here. Okay, cryptanalysis, and it should go down eventually. There we go. All right, let's just try the cryptanalysis and see if it has that default data there. So, going back to Cryptool, whenever my laggy system is going to respond here. Right, I'll minimize this one then. Maybe that will get it out of my way. There we are. All right, so now I do, whoa. Whoa! Oh, it's responding slowly to clicks I've made. Okay, now, go to my wizard, do cryptanalysis. I just have to move a little slowly with this cloud machine through the City College network. All right, so I'm going to do classic encryption, Caesar, there we go. And now, this will do, this is German input, which I think is in fact a quote from the original Caesar. And it will scramble it here and turn it into, so, oh, I have ciphertext, pardon me, it's doing decryption. So this stuff is scrambled, and it's in German, and it's going to decipher it automatically and get it down here. And if you want to see how it did it, you can go down here and see the attack. Yes. There we go. It did it by frequency analysis. So here they are, and in German, the most common letter is J. So that's why it needed to know the language. So it just did frequency analysis, and it deduced the key from that. And so there's a project you can do here. Let me try opening it up here since I'm having so much lag there. All right, so I got some challenges, and you can use that tool to crack some of these. So it cracked it with that. So here's a paragraph. You can crack this. You'll be able to crack this with that tool. It's a whole long paragraph, so it's got enough evidence. So you'll be able to, the flag is the author of the quote. Here's a shorter English sentence. This one here, the automated frequency analysis will fail because it's too short. So there are various ways to do it. What they say here is you can just try the likely shift values and test them one by one, or you could just use that Python program from class that does a brute force attack, trying all possible shifts. And here's a song lyric. And this one here is not only short but repetitive. So it's going to be very hard to crack. And you could, again, do it with brute force, or you could hunt for an online tool that does a better job. But anyway, there's a few challenges with the Caesar cipher. And in the same tool, you can also do the substitution cipher, which is a generalization of the Caesar cipher, where you don't just shift everything forward so many letters in the alphabet, you just have each letter replaced with another random letter with no pattern. And that, by the way, is worth talking about. You might think that is secure because the actual number of possible keys is very large. Let me make a blank page and put it up here. So let's consider that. If I try to make a substitution cipher, I have like A, B, C, and I turn that into like 3 random letters. And these can be anything. If you think about it, there's 25 possible ways I could replace the first character if I don't duplicate. Really, there's 26 if I consider duplication. Then there's 25 ways I can do the next letter. Then there's 24 ways I can do the next letter. So the total number of keys is 26 factorial, and that is a really big number. So you might think this is really secure. The problem is, so just by key size, it looks secure. You could never try all possible keys. But the problem is it will fall to frequency analysis. All you have to do is find the most common letter, and that's probably E. And the next one is probably T. And after you get a couple letters, then you can look for short words, and one of them is going to be the. And that's why children break this one with no math at all, by hand, with no computer at all, in cartoons. So even though the key size is enormous, the algorithm is so weak that there are other ways to deduce information without finding the key. So it's another example of this kind of flaw. So anyway, here's the monoalphabetic substitution.
If you had Vigenère on top of that, it's actually no more secure than Vigenère. It's probably mathematically provable that it's exactly as weak or as strong.
Well, no, I think I think Vigenère is weaker because the key space is only 26. And if you had a key of like 5, so Vigenère is definitely weaker. It would be faster to crack.
What I'm saying is you take substitution cipher and add a Vigenère.
Right, and add a Vigenère type key, then it would get stronger. It would now be harder to do frequency analysis. For example, you'd need longer plain text. Because if you had a 3-letter key, you'd need the plain text to be 3 times longer anyway. So that's some strength. But that's right, you can do that. Now the thing there's another one, I forget the name of it, which is actually pretty strong, very hard to crack, where what you do is you have send the troops in Monday. You have a message like this. What you do is you encrypt the first letter with the Caesar cipher, and then you use this letter of the message of the plain text as the key. This one, so the key keeps changing. This one is actually very hard to crack.
Yeah.
And I think it might even be considered pretty strong.
Did you crack that from Putin's cell phone?
yeah, that must be it. Yeah.
Does the encryption itself have to be in some sort of order, or can it be random?
Well, it can't be random. See, if you encrypt something with randomness, you can never decrypt it. So there must be a pattern. There must be a system.
Oh, so you can predict it when no one else can.
That's right. And so now anybody with the key can decrypt it. So you give the other person the key, and now they can read it.
But they don't even need a key. They can just predict it.
Well, that's the problem. But for a secure system, they could only decrypt it if they had the right key. For an insecure system, like these Caesar ciphers, you could decrypt it without the key, and then it's not good. Yeah. So what you want, that's why AES is the modern system recommended. You have a key, and if somebody doesn't have the key, they really can't get in. Not unless they can guess the key or steal it or something. So,
from a pure information theoretical standpoint, you can't have signal to noise ratio of 0. but you want it to
That's right.
approach zero as much as possible.
That's right. What you want is it to be impossible in practice to find the pattern in the ciphertext, but there must be one there. It came from a key. And so you've tried to hide it in the math to where nobody can find it. And they've gotten pretty good at that, but there's no guarantee. Somebody could find a mathematical trick to crack AES, and there's no way to be sure that won't happen.
I think as long as it has to be in some sort of order,
Yeah.
it can never be fully foolproof.
Though that's, in principle, you might be right. This is closely related to the P equals NP problem that we'll get to. The question is, are any mathematical problems really hard? And no one really knows. All encryption is based on the idea that if you make it hard, nobody can do it. But people keep thinking of new clever tech tricks, so what used to be hard becomes easy. And so the question is there anything that is just really intrinsically hard that could never be made easy and no one knows?
As long as it's predictable or it's in some sort of order, I don't think it can be foolproof.
Yeah, well, that's the issue. But right now we're using stuff that seems to be good enough, but we don't know that it's perfect. These are very good points. Anyway, so this one here, you use a you monoalphabetic substitution. So you can see here, it's going to crack it, and it takes a while longer to crack this. It has to do a more complicated attack. But it will use various attacks, a dictionary attack, a genetic attack, where it modifies things and so on. And so you can try cracking a few of these with that tool if you like to. Anyway, so these are things where you get to practice using that simple tool. If you don't want to do any of these projects, like for example, if you don't have a Windows machine and you don't feel like getting one, you can just skip these and do extra credit projects. There's a lot of other extra credit projects available. Just make up the points somewhere else. But anyway, you might want to try that Windows tool if you'd like a gentle introduction to some of these algorithms and you don't want to even have to write into a Python code or anything.
I wonder if it can be hidden under a layer of randomness.
Under what?
Under a layer of randomness.
Well, that's essentially what the encryption algorithms do. AES creates a key stream that looks random, so it's like a one-time pad. But the key is shorter. So it's not as perfect as a one-time pad, but all the encryption regimes are essentially imitations of a one-time pad, where you create a random-looking bit stream to encrypt with, but it's not really random, it's all generated from a key. So that you have a lesser key distribution problem. These are good questions. I'm going to stop this recording.